Okay, so in this section we're going to talk about work, obviously. So I hope you don't mind that I've written some bullet points up here before starting the video, and this would probably now be a good time to pause the video and jot them down. All right, so this gives us some talking points through which we can describe work. And work, really in the most basic definition, is a force times a distance, or some integral of F ds. In the context of this course, it is a means by which we transfer energy to or from a system. Work is done by a system on its surroundings if the sole effect on everything external to the system could have been the raising of a weight. So the easiest way to think about this perhaps is if I have a system, say a little engine or something, that's turning a shaft, okay? So the turning of that shaft is doing some work. Well, I can measure the amount of work that system will do over a period of time if I were to connect a pulley system with a weight and raise the weight. That'd be a very, very basic, very simple way to quantify the work done by the system. So as we get into a little bit more complicated sort of boundary work or different particle interactions, I think this definition gets a little bit more difficult to visualize, but it nevertheless does hold true. Work is not a property. So energy is a property, pressure, temperature, volume, all those are properties. Work is not a property. And it's not a property because work at a state has no meaning. We can't say that a system has so many joules of work. No, we can say a system has transmitted so many joules of work or transferred so many joules of work, or we had X number of joules transmitted to a system. And work is path dependent. So recall that properties must be path independent. But work is path dependent. It relies on some force executed over some path which can be quantified. So we'll get into a little bit more about this path dependency later on. So more than just turning a shaft, we can think about work in terms of expansion or compression of a system or compression of a boundary. For example, if you're blowing up your bicycle tires with a traditional pump, as you depress the pump, you're compressing that air. You're doing work on the air. You're providing a force over a distance. So you're doing compression work on that gas. So let's depict this with a simple diagram. I do apologize for my lack of artistic ability. So let's say now that we are looking at this tube, and in the tube we've got a piston. Okay. So we apply a force to this piston, which of course we could define that force as equal to some pressure times an area. And we move this piston from point 1 to point 2. Okay, so we've moved this this piston some delta x from x1 to x2. We've applied a force over a distance. All right, so as we shrink that distance down, we can say that the differential change, or the differential amount of work that I provide to this piston or this boundary is going to be equal to the pressure over which I apply an area over which I apply a pressure, so P times an A times dx. Okay, so I can see that an area times some dimension this way is equal to a volume. In fact, it's equal to a differentiable volume if I have a dx. So I can write this as P dV. All right? So if I take the integral of work and P dV, so the integral of delta W times the integral of P dV. Whoop. Sorry for my slop. And in this course, I will denote volume, capital V, as a V with a line through it, not to be confused with lowercase v's, which we will see later. All right, so this will go from volume 1 to volume 2. Okay, so let me now rewrite this integral of delta W as just W now. This is what we call boundary work. And because of its definition, boundary work must occur at a boundary, and it can only occur when my boundary moves. Okay, so now a little bit of space. I've rewritten my expression for boundary work up here at the top. Of course, the limits of this boundary work are from V1 to V2. Now, if I have a constant pressure, I can pull P outside my integral. And then I can write boundary work as P V2 minus V1. Okay. Now sometimes I can treat pressure as constant if I have a quasi-equilibrium process. We talked about quasi-equilibrium in the last chapter, but let's quickly state it here again. Quasi-equilibrium All right, so quasi-equilibrium process is one in which departure from thermodynamic equilibrium is at most infinitesimal. Okay, so continuing our discussion of boundary work, let's consider this tube or piston cylinder sort of assembly here, where we've got this piston that is holding back some gas. All right. Now, let's call this state 1, or state 1 at position x1, and this is going to be state 2. So to get from state 1 to state 2, the volume of my gas is going to increase. The gas is going to push the cylinder along the tube to state 2, and while doing so, it's also going to decrease pressure. All right. So what does that look like on a pressure volume diagram? We'll do many of these in this course. We'll call them PV diagrams. Okay, so we're going to start at some volume 1, V1, and we'll give it some pressure P1. Okay. All right, and kind of generally over here, we're at lower pressure, higher volume. So there we go, V2 and pressure P2. So let's say that our pressure curve looks like that. So all this area under this curve is my boundary work. It's the integral of P dV. Okay. So this demonstrates the path dependence of work. Perhaps I can make that even more clear if now I've got a PV diagram again. Same sort of thing, point 1, point 2. Let's call this this original path that I drew path A. Okay. So we're going from 1 to 2 on path A. Maybe instead I get from 1 to 2 via path B. Well, because the area bounded by path B is bigger than that bounded by path A, I would have to produce, or my gas would have to do more work to get from state 1 to state 2 versus if it had traversed path A. Work is path dependent. Okay, so I think the last topic of this section will be spring work. So allow me just to put that down here. So spring work, we'll denote that with a W as well. that is going to be, of course, it's a force times the distance, but remember, for springs, or at least Hookean springs, force is K times X, where K is a spring constant. So I'm going to be doing the integral of some force over some distance dx. So maybe that's from x1 to x2. So I'm going to replace F with Kx. And of course, if K is constant over my range of X values, I can write spring work as 1/2 K x2 squared minus x1 squared. And that should do it for work for now.